Welcome to The Explainer. Today, we're diving into something that's totally invisible but runs basically everything, the database. We're going to talk about how we take all this mess of information and turn it into something clean, organized, and super powerful. I mean, really think about it. You book a flight, you check your bank account, you toss something in your shopping cart. You're tapping into these massive systems that are juggling just insane amounts of data every single second. So how in the world does all of that not just completely collapse? Okay, so let's start somewhere we've all probably been. You've got a project, or maybe you're trying to track your spending. What do? You fire up a spreadsheet, right? And hey, for a little while, it works just fine. But pretty quickly, you hit a wall. As you can see here, tools like spreadsheets just have some major limitations. The second you start dealing with thousands of records, let alone millions, they just bog down. They get so slow. And what happens if you need to add a new column or change something fundamental? Oh, it's a total mess. And security? Backups? Yeah, good luck. You're pretty much on your own. The bottom line is they just aren't designed for the kind of heavy-duty work our world demands. So this is where we need to throw that whole idea out and start fresh. We need something totally different, something built from the ground up specifically to handle massive amounts of data. And that, my friends, is the Database Management System, or DBMS for short. And no, a DBMS is not just a spreadsheet on steroids. It's a whole different beast. It's this dedicated piece of software that's like an incredibly smart gatekeeper for all your information. The analogy of a super-powered librarian is perfect. This librarian doesn't just know where every book is. They enforce the rules, they check your ID for security, and they make sure nothing gets lost or messed up. It's a complete system. So what's the secret sauce here? Well, for most of these systems, it's something called the relational model. And the idea behind it is actually, beautiful in its simplicity. Instead of having one giant, chaotic spreadsheet, you break everything down into these small, clean, organized tables. And each table is dedicated to just one specific thing, like students or courses or whatever. And this right here is a perfect picture of what I'm talking about. This is called a database schema, in this case for a university. See those boxes? Student, course, instructor. Each one is its own tidy table. And those lines connecting them? That's where the magic happens. Those are the relationships. This schema, it's literally the architectural blueprint for how all the information fits together. Okay, so you've got all these tables. How do you make sure you can find, say, one specific student out of thousands? That's where the primary key comes in. Every single row in a table gets one. You can think of it like your own unique student ID number. It's the one thing that guarantees you're looking at that student and not some other one. Absolutely no duplicates allowed. All right, so primary keys give everything a unique identity. But how do we link things together? How do we say this student is taking that course? Well, that is the brilliant job of the foreign key. It's basically a special field in one table that just points to the primary key in another table. It's the magic glue. It's what draws those lines on the blueprint we just saw. It's how we connect the dots. Okay, this is great. We've got this amazing, organized structure of tables all linked together. Now what? How do we talk to it? How do we ask it a question? Well, we use a special language. It's called SQL. That's SQL for Structured Query Language. And don't let the name intimidate you. It's actually designed to be pretty easy to read, almost like English. It's the universal language for talking to these kinds of databases. Let's just walk through a super simple example. So here's our course table, right? Got the title, the department, all that stuff. And let's say we have a question. We just want to know what courses are in the biology department. In SQL, that question looks just like this, and you can almost read it like a sentence. Select title, that's what we want to see. From course, that's where to look. And where department name equals biology, that's our filter. It's just a very specific, logical way of asking. And bam, just like that, the database goes to work, zips through all its records, and hands you back exactly the list you asked for. No extra junk. It's incredibly precise and ridiculously fast. But here's where SQL gets really powerful. Its true superpower is joining different tables together. So now we can combine info from our course table and, say, a prerequisites table to answer a much more interesting question, like, hey, what classes do I have to take before I can get into genetics? That's the kind of thing that's almost impossible with a spreadsheet. Okay, but here's the catch. All this incredible power, The speed, the connections, the fancy queries, it all falls apart if the database isn't designed well from the very beginning. You can't just start throwing data into tables and hope for the best. You really have to think like an architect. Because if you don't, you run into these nasty problems called anomalies. And that's just a fancy word for when your data starts to contradict itself. Imagine you need to update someone's address, but because of a bad design, their address is stored in 3 different places. You update 2, but you miss the 3rd. Now what? Your database is literally lying to you. It's a huge problem.
Just look at this table here. This is a perfect example of a flawed design. See how the city, Delhi, is repeated over and over and over again for every single part from that one supplier? That's what we call redundancy. And it's a ticking time bomb. What if that supplier moves? Now you've got to hunt down every single one of these rows and change it. If you miss even one, your data is wrong. It's a total recipe for disaster.
So, how do you prevent that mess? Well, database designers follow a process with a fancy name: normalization. The best way to think about it is like a set of building codes for your data. The whole point is to eliminate that dangerous repetition. You basically follow a few steps to break down big, clunky tables into smaller, more logical ones. Step 1, make sure every cell holds just one piece of info. Step 2 ensures everything in a row is directly related to the main key. And Step 3 gets rid of any weird roundabout dependencies. By doing this, you build a database that's lean, efficient, and, most importantly, reliable.
Okay, so we've gone through tables, keys, the SQL language, design rules, a lot of technical stuff. So why should you care? What does any of this have to do with your actual life?
Well, it matters because pretty much everything you do runs on this stuff. The bank that holds your money, it's all managed by a database. The airline you fly with, their entire reservation system is a massive database. Universities, online stores, your company's HR system, they are all powered by these silent, invisible engines working in the background, all built on these very principles. So there you have it. Our digital lives are literally built on a foundation of well-designed databases. But, the story doesn't stop here. The big question now is, what's next? We're seeing this absolute explosion of what's called unstructured data. All the text messages, the photos, the videos. Figuring out how to organize that is the next great frontier. The core ideas of bringing order to chaos are more critical than ever, and how we tackle that is absolutely going to define our future.